Now, what I'd like to do is to eventually take the limit as n goes to infinity here. And the quantity that's hard to understand is this massive quantity here. And there's one change that I'd like to make, but it's a very modest one, extremely minuscule, which is that I'm going to write 1, just to see that there's a general pattern here, I'm going to write 1 as 1 squared. And, well, let's put in the 3 here, why not? And now I want to use a trick. This trick is not completely recommended, but I will say a lot more about that when we get through to the end. I want to understand how big this quantity is, so I'm going to use a geometric trick to draw a picture of this quantity. Namely, I'm going to build a pyramid. And the base of the pyramid is going to be n by n blocks. So imagine we're in Egypt and we're building a pyramid, and the next layer is going to be n minus 1 by n minus 1. So this next layer in is n minus 1 by n minus 1. So the total number of blocks on the bottom layer is n squared. That's this rightmost term here. But the next term, which I didn't write in, but maybe I should, the next to the last term was this one. And that's the second layer that I've put on. Now this is the, if you like, the top view. But perhaps we should also think in terms of a side view. So here's the same picture. We're starting at n, and we build up this layer here. And now we're going to put a layer on top of it, which is a little shorter. So the first layer is of length n. And the second layer is of length n minus 1. And then on top of that, we have something of length n minus 2, and so forth. And we're going to pile them up. So we pile them up all the way to the top, which is just one giant block of stone. And that's this last one, 1 squared. So we're going backwards in the sum. And so I have to build this whole thing up. And I get all the way up in this staircase pattern to this top block up there. All right, so here's the trick that you can use to estimate the size of this. And it's sufficient in the limit as n goes to infinity. The trick is that I can imagine the solid thing underneath the staircase, like this. That's an ordinary pyramid, not a staircase pyramid, which is inside. And this one is inside, and so, but it's an ordinary pyramid as opposed to a staircase pyramid. And so we know the formula for the volume of that, because we know the formula for volumes of cones. And the formula for the volume of this guy, of the inside, is 1/3 base times height. And in that case, the base here, so that's 1/3, and the base is n by n, right? So the base is n squared. That's the base. And the height, it goes all the way to the top point. So the height is n. And what we've discovered here is that this whole sum is bigger than 1/3 n cubed. Now, I claim that this line, by the way, has slope 2. So you go half over each time you go up 1. That's why you get to the top. On the other hand, I can trap it on the outside too by drawing a parallel line out here. And this will go down a half more on this side and a half more on the other side. So the base will be n plus 1 by n plus 1 of this bigger pyramid, and it'll go up one higher. All right? So on the other end, we get that this is less than a third n plus 1 cubed. Again, n plus 1 squared times n plus 1. Again, this is a base times a height of this bigger pyramid. Yes, question?
It seems like you're adding up areas with the white in the center of your inequality and then equating it to volume.
The question is, it seems as if I'm adding up areas and equating it to volume. But I'm actually creating volumes by making these honest increments here. That is, the base is n, but the height is 1. Okay? Thank you for pointing that out. Each one of these little staircases here has exactly height 1. So I'm honestly sticking blocks there. They're sort of square blocks, and I'm lining them up, and I'm thinking of n by n cubes, if you like, honest cubes there. And the height is 1, and the base is n squared. Okay? All right, so I claim that I've trapped this guy in between two quantities here. And now I'm ready to take the limit. If you look at what our goal is, we want to have an expression like this, and I'm going to, this was the massive expression that we had, and actually, I'm going to write it differently. I'll write it as b cubed times 1 squared plus 2 squared plus n squared divided by n cubed. I'm going to combine all the n's together. All right? So the right thing to do is to divide what I had up there, divide by n cubed in this set of inequalities there. And what I get here is a third is less than 1 plus 2 squared plus 3 squared plus n squared divided by n cubed is less than 1/3 times n plus 1 cubed divided by n cubed. And that's a third times 1 plus 1 over n cubed. And now I claim we're done, because this is a third, and the limit as n goes to infinity of this quantity here is easily seen to be, this is, as n goes to infinity, this goes to 0. So this also goes to a third. And so our whole total here, so our total area under x squared, all right, which we sometimes might write the integral from 0 to b x squared dx, is going to be equal to, well, it's this 1/3 that I've got, but then there was also a b cubed there. So there's this extra b cubed here. So it's a third b cubed. That's the result from this whole computation. Yes, question? So that's a very good question. The question is, why did we leave the b over n cubed out for this step? And part of the answer is malice aforethought. In other words, we know what we're heading for. We understand this quantity. It's all one thing. This thing is a sum which is growing larger and larger. It's not what's called a closed form. So the thing that's not known or not well understood is how big is this quantity here? 1 squared plus 2 squared, the sum of the squares. Whereas this is something that's quite easy to understand. So we factor it out, and we analyze carefully the piece which we don't know yet how big it is. And we discover that it's very, very similar to n cubed, but it's more similar to 1/3 n cubed. It's almost identical to 1/3 n cubed, this extra piece here. So that's what's going on, and then we match that. Since this thing is very similar to 1/3 n cubed, we cancel the n cubes, and we have our result. All right. Let me just mention that although this may seem odd, in fact, this is what you always do if you analyze these kinds of sums. You always factor out whatever you can, and then you still are faced with a sum like this. So this will happen systematically every time you're faced with such a sum.